All right, this review is for Chapter 9. This is the no proportions review, and proportions will come in at a later date. So this is just Chapter 9, Section 1 and Section 3. All right, so starting off on the review. All right, first it says state the hypotheses, and it says state the appropriate null and alternate hypotheses in each of the following cases. It says the average height of 18-year-old American women is 64.2. You wonder whether the mean of this year's female graduates from a large local high school differs from the national average. So differs just means not equal to. It does not mean we assume it to be lower or higher. So you measure an SRS of 48 and find X bar is 63.1, which doesn't help us set up our null. Okay, so as the kids call it, the ho and the ha. Make sure you use mu here, not X bar. Okay, so in each case, we're looking for the true mean. All right, and we go with the previously known value of 64.2. That's the claim. And then what we're checking for is to see if it's still the same, which is a not equal to test. Sometimes we assume that it's greater than or less than, but that's it. Now, what does mu actually represent? Mu is the true mean, okay, and it is the mean height of females. All right, there we go. Let's go to the next one. 9.2, eye black. Athletes performing in bright sunlight often smear black grease under their eyes to reduce glare. Does eye black work? In one experiment, 16 randomly selected subjects took a test of sensitivity to contrast after 3 hours facing into bright sun, both with and without the eye black. All right, so the N is 16, all right? Okay, here are the differences in sensitivity with eye black minus without eye black. All right, so again, our N was 16. All right, and there should be 16 values there. We want to know whether eye black increases sensitivity on the average. So we're going to treat a positive value, okay, as good, meaning the eye black worked. Okay, now that is not entirely intuitive, so I'm helping you out with that a little bit there, okay? So they should have mentioned like how that actually is measured and everything, because I don't think it's perfectly clear. But a positive number, okay, means that the eye black worked. So here it worked, did not work. So here without the eye black was better, and so on, okay? So what that means for our null and alternate hypotheses, okay? So for part A, our null is that the mean difference, okay, is 0, which means there's no difference between using it and not using it. The alternate, the mean difference, okay, is going to be greater than 0. Okay, so again, greater than 0 means the eye black worked. So that's the kind of test that we're going to run there. All right, now what? Now we take all these values, okay, we type them into the calculator, all right, and oh, I need to define mu d. Okay, so mu d is going to be the true mean difference, okay, in contrast or sensitivity. Let's do insensitivity, and it's defined as eye black minus not eye black. Okay, and if you want, you could rephrase that the positive means the eye black worked. Okay, all right. So there's a description of those. Part B says check the conditions for carrying out a significance test. All right, the 3 conditions we're supposed to have are random, and they said that they did an SRS. We're supposed to have independent. Okay, so did we have independence? So this is going to be less than 10% of the actual population, so we're good there. And then normal. And so as long as we don't have any major outliers, we're probably okay to proceed. They didn't say that it was normally distributed, Okay, but we're probably going to be okay to go with that. All right, so good. Again, part B is AP only. All right, C, the p-value of this test is 0.047. Interpret this value in the context. Okay, so if p-value equals 0.047, it says if the difference equals 0, okay, if the mean difference equals 0, then the chance of the data, so giving x bar as it did is only 0.047. So you start off saying the mean is, or excuse me, the null is true, and the chance of getting the statistic that we got, in this case x bar, is going to be the p-value. All right, let's look at the next one, strong chairs. It says a company manufactures classroom chairs for high school students, claims that the mean breaking strength of the chairs is 300 pounds. Okay, one of the chairs collapses beneath a 220-pound student last week. You wonder whether the manufacturer is exaggerating the breaking strength of the chairs. Okay, so we are assuming that the true mean is less than what they're claiming. All right, so state the null and alternate hypotheses. So for part A, okay, our null in this case is going to be that they are right. The claim is that the mean is 300, and our assumption, our alternate hypothesis, is the mean is under that. Okay, and define mu. Mu is the true mean breaking weight. Okay, part B. Describe a type 1 and type 2 error. All right, so every time I see one of these, I write 1, 2. Okay, and I know that 1 starts with null true. Okay, found false. So we reject a good null. All right, and here we go the opposite. Null false. Okay, found true. So technically we reject or not reject, so using true and false is not technically the best way to describe it, but this reminds me how to do it. So in this case, the null is true. So the mean breaking weight is 300, but we think that they're wrong and we reject that in favor of thinking that their chairs break with a lower weight. Okay, the null is false. So the mean is not 300. The mean is really truly under 300, but we do not find that it is under 300. So we did not reject the null when we should have rejected the null. All right, part C. Would you recommend a significance level of 0.01, 0.05, or 0.10 for the test? Justify your choice. Okay, so in this case, I would just use, well, it depends on what you want. If you are trying to show that the go-to standard is 0.05, so might as well just stick with that. Unless we have reason to change it off of 0.05, I would just stick with the standard. All right. The power of the test to detect the mean of 297 or 294 is 0.71. Explain what this means to someone who knows little statistics. Okay, so the chance that we reject is 0.71. Power is the chance that we reject a bad null. Okay, explain 2 ways that you could increase the power of the test from D. Okay, our 2 go-tos, if we're trying to reject a bad null, to make that easier, we would increase sample size, or we would use a larger alpha. Okay, so if we go from 0.01 to 0.05 to 0.10, all of those jumps make it easier to reject a bad null because it's less strict in terms of our criteria. A large company medical director launches a health promotion campaign to encourage employees to exercise more and eat better. One of the measures of effectiveness of such a program is a drop in blood pressure. The director chooses a random sample of 50 employees and compares their blood pressure from physical exams given before the campaign and again a year later. The mean change after minus before in systolic blood pressure for these 50 employees is -6, and the standard deviation is 19.8. Okay. Do this data provide convincing evidence of an average decrease in blood pressure among all of the company's employees during the year? Carry out a test at the 0.05 significance level. All right, so for number 6. Okay, first, our n is 50, which means our degrees of freedom is 49. Okay, our x bar is -6. Okay, and we have a s of x of 19.8. Okay, all right, so we're going to have to also find s of x bar, but we also want to identify the null and the alternate hypotheses. Okay, so just listing all the things that we've had. We also had an alpha of 0.05. All right, next. What we're tracking here is a mean difference because we're tracking the after minus before. Okay, so after minus before, we want to see a drop. Okay, so after minus before, you would hope this would come out negative, which means that we're subtracting a larger value. So if someone dropped their blood pressure, then the after value should be less than the before value, therefore creating a negative number. Okay, so that's the goal. And that would be the point of the campaign. So what we do is we test that versus 0. The mean difference is equal to 0, and the mean difference is less than 0. Okay, where the mean D equals the true change in blood pressure. The true mean change or difference in blood pressure. Okay, so we're going to run the test now. Okay, so when I bring up the calculator, all right, and we're going to run it. So program AP stats. Okay, now I go to the next menu, go down to hypothesis test, and I'm testing a mean. The null mean here is 0. The sample mean is -6. S of x is 19.8, and the sample size was 50. Okay, so should we run a ZRT? So they didn't tell us the standard deviation of the population, they told us the standard deviation of the sample, so we don't know sigma, so we have to use a t-test. All right, in this case, we had the standard deviation of x bar to be 2.8. Our t-value is -2.14. The degrees of freedom was 49, which you already had. And because it's a one-sided test, we just use the p-value, 0.018. Okay, so let's make our conclusion. And our conclusion is the meaning of the p-value. Let's do that. Okay, if there's really no change in blood pressure, then the chance of having an x bar of -6 is less than 2%. Okay, and because we're at a 5% alpha level, this is more rare. So we will then reject 0 as the change. So it appears, so we reject the null, it appears the program lowered blood pressure. There we go. All right, so there we go. Okay, let's look at 7. Seven says, font and reading ease. Okay, and it says, does use of fancy type fonts slow down reading of text on a computer screen? Adults can read 4 paragraphs of text in the Common Times New Roman font in an average of 22 seconds. 4 paragraphs in 22 seconds, that seems fast. Researchers asked a random sample of 24 adults, okay, to read this text in an ornate font named Gigi. Here are their times in seconds to read the same thing. Okay, do these data provide good evidence that the mean reading time for Gigi is greater than 22 seconds? Carry out an appropriate test to help you answer this question. All right, so in 7, what we're going to have is the null and the alternate, okay? And what we find from the null and the alternate, the claim is that the mean time is 22 seconds. And what we're looking at now is whether or not it takes them longer. So the assumption is that a fancy typeface slowed down the reading. Okay, slow down means takes more time. So we would think that the mean would be greater than 22. Okay, define mu. Mu is the true mean time, seconds, in seconds, to read 4 paragraphs. Okay, there we go. Now, how do we find that? Well, all of these values, okay, and there's 24 of them, would go into L1. So when you run those in L1, okay, and then you run basic stats on L1 and make sure it goes in L1, we're going to find that the X bar is 26.496. The S of X equals 4.728. With an N of 24, our degrees of freedom is 23. 23. Okay, and now we need to describe standard deviation of X bar, which is this divided by the square root of 24. And when we do that, I didn't write that down. Let's calculate that. Okay. So we have 4.728 divided by the square root of 24. Okay, so there's my calculation. And this value is 0.965. Okay, so the calculator gives you that. So when you run the test from the calculator, let's just show how to do that piece. So I didn't show the basic stats part, so we should be able to get to these three pretty easy. All right, so if I run AP stats, now I go to a hypothesis test, test it on a mean. The null mean in this case is 22. Okay, the sample X bar is 26.496. S of X is 4.728. N is 24. Okay, and we're going to run a t-test. So when I do that, there's the same standard deviation of X bar. Okay, t-value is 4.658, which is pretty large. And you're going to now find a p-value of 5.45 times 10 to the negative fifth. So it's essentially 0. Okay, so if the true mean is 22, then the chance of getting an X bar at 26.496 is almost impossible. Therefore, this is wrong. Okay, and the way we say that in statistical language is that we reject the null because 0 is less than 0.05. Okay, and so therefore it appears that people read slower with fancy fonts. So people appear to read slower using fancy fonts. Okay, there we go. Okay, looking at 8. Radon detectors. Radon is a colorless, odorless gas that is naturally released by rocks and soils. Okay, because radon is slightly radioactive, there's some concern, maybe a health hazard. Radon detectors are sold to homeowners worried about this risk, but the detectors can be inaccurate. University researchers place a random sample 11 detectors in a chamber where they're exposed to 105 picocuries per liter of radon over 3 days. A graph of the radon readings from the 11 detectors shows no strong skewness or outliers. The Minitab output below shows the results of a one-sample T interval. Okay, so here's where we are. Okay, all right. Is there significant evidence at the 10% level that the mean reading mu differs from the value of 105? Give appropriate evidence to support your answer. Okay, so first of all, N was 11. Okay, the mean was here. That's X bar. Standard deviation is here. The standard deviation, standard error of the mean is basically the standard deviation divided by the square root of 11. So that's handy. And they give us a 90% confidence interval that is here. Okay, all right. So the question is, if it's a 90% confidence interval, okay, significance at 10% level, what we're going to look for is the 105 inside of the confidence interval. And the interval went from 99 to 110. So 105 is inside of that. So since the 105 is inside of that, we would not reject the mean. It appears that 105 is okay. So 105 is inside of here. Therefore, okay, we failed to reject. Doesn't mean that the testing is correct. It just means that we don't have evidence to reject that claim. All right, got it. Okay, 9.9 says better barley. Does drying barley seeds in a kiln increase the yield of barley? A famous experiment by this dude. Okay, investigated this question. 11 pairs of adjacent plots were marked out in a large field. For each pair, regular barley seeds were planted in one and kiln-dried seeds were planted in the other. The following table displays the data on yield. Okay, how can random conditions be satisfied in this study? You would randomly assign the regular versus the kiln on the two plots. So you would have that randomly assigned. Okay, so random assignment of treatments would be how we would do that. Okay, perform an appropriate test to help answer the research question. Assume the random condition is met. What conclusions could you draw or would you draw? All right, so first, we would take the difference of all of these, and that's what we want. So when you find the difference of all of these, okay, that's the values that would go into the calculator. All right, one quick easy way to do that is to type all of those values into L1, L2. The confidence interval will do that as well, or we can just do it as a matched pair test. So I'm going to type all of those in and just run a matched pair test, which is what we're doing. All right, so stat, edit. Okay, so I've typed in all of these values, okay, into the stat list in L1 and L2. And they do have to stay side by side and correct, so hopefully we typed them all in the right spots, and they're all correct. So program, AP stats, okay, when I go to the hypothesis test, what I'm actually running is a test on L1, L2, and it's a paired test. Okay, so we're doing a matched paired test. All right, the null difference is 0. Okay, so the null is that the mean difference equals 0, and the alternate is that the mean difference is what? So what we're looking for here is whether or not the assumption is that the kiln data is better, has more yield than the regular data. So if this has more yield, it is larger. And if we're subtracting a regular minus kiln, okay, then we'll end up with a negative value. So negatives for the difference means that the kiln was better, because when we subtract, we would subtract a larger number. Okay, so less than 0 would be our test. Okay, where mean D is the difference, the true mean difference in yield, and it's regular minus kiln. Okay, all right, so let's run it. Okay, so our mean difference here is x bar equals negative 33.7. Okay, the standard deviation of x bar is 19.95. We've got a t of negative 1.69, degrees of freedom 10, and we ran it as a one-sided test, so the p-value 0.06. Okay. All right, so what level did they tell us to run this at? Did they say the alpha level in this case? They didn't say. Therefore, we assume that the alpha is 0.05. Okay, and we are not below that. We have a 6% chance of getting the x bar this far away from 0. Okay, we needed to have a 5% or less in order to reject, so we fail to reject. All right. Okay, let's look at the multiple choice ones. All right. You were thinking of conducting a one sample t-test about the population mean. Using 0.05 significance level, you suspect that the distribution of the population is not normal and may be moderately skewed. Which of the following statements is correct? Okay, You should not carry out the test because the population does not have a normal distribution. Not necessarily. Okay, so sample size will tell us that. And they didn't say there's any outliers and stuff, so as long as sample size gets pretty good, we'll be all right. You can safely carry out the test if your sample size is large and there are no outliers. Yeah, there it is. Okay, so that's the one we want. Okay, B. You can safely carry out the test if there are no outliers. Regardless of sample size, no. Carry out the test if the population standard deviation is known, no. Okay, so if the population standard deviation is known, it would be a z-test, but we still want to have a sample size large enough. Okay, the T procedures are robust. You can use them anytime you want. Not true. Okay, so again, skewness can mess it up if you have a small sample size. So you need a large sample size. All right, 3. To determine the reliability. Oh, this one is a proportions test. Okay, so we're going to 4. 4 is down here. Okay, significance test allows you to reject a null hypothesis, okay, in favor of an alternate at the 5% significance level. What can you say about significance at the 1% level? Okay, H sub 0 can be rejected at the 1% level. Not necessarily. Okay, there's insufficient evidence to reject this at the 1% level. It depends. As long as the p-value came out below 1%, it would be rejected at both levels. So they didn't tell us anything about the p-value. There's sufficient evidence to accept. No, we don't know that either. H of A can be rejected. We never reject the alternate. And then the answer can't be determined. Yeah, we don't know enough information. We need to know the p-value in order to answer this question. All right, 6. A researcher claims to have found a drug that causes people to grow taller. The coach of a basketball team at this university expressed interest but demands evidence. 1,000 Brandon students volunteered to participate in an experiment to test this new drug. 50 of the volunteers are randomly selected. Their heights are measured and they are given the drug. Okay, 2 weeks later, their heights are measured again. The power of the test to detect an average increase in height of 1 inch could be increased by, okay, so power is rejecting a bad null, okay? And if you want to make it easier to reject a null, the two things that do that are the sample size going up and the alpha level going up as well, okay? So you'd be less strict on the conditions, so the alpha level can be less strict, so going up, and we would have more sample size causing, again, if we're rejecting a bad null, then more data should make it easier to do that, okay? So the value here that is doing that is C. Okay, so the alpha level 0.05 instead of this. That is true. Okay, all right, 7. 95% confidence interval for a population mean mu is calculated to be this. All right, so we've got a 95% confidence interval. There's the interval. Assume the conditions for performing inference are met. What conclusions can we draw for a test at the null is the mean is 2 versus the alternate is it's not 2 at the 0.05 level based on the confidence interval. All right, first the 0.05 level here and on a two-sided test, okay, is the same as the 95% confidence interval. So they will give us the same results. So we're okay there. If it's a one-sided test, that's not true. So on a two-sided test, we're okay. All right, so 2. What we would look for is 2 inside of the interval. And 2 is inside the interval, so we cannot reject it. Okay, so we would fail to reject. Okay, all right, so in 7, none, we cannot carry out the test, not true. Okay, B, none, we can draw none. Okay, so here we go. E, we would fail to reject it at the alpha equals 0.05 level. That is true. Okay, so our answer to that one was E. All right, the next one we're going to go to is 9. Okay, 9 says a simple random sample of 100 postal employees found that the average time these employees had worked at the postal service was 7 years with standard deviation 2. Okay, so we've got a mean standard deviation. Do these data provide convincing evidence that the mean time of employment mu for a population of postal employees has changed from the value of 7.5 that was true 20 years ago? To determine this, we test the hypotheses that the average is 7.5 versus it's not 7.5, so it's a two-sided test. Using a one-sample t-test, we conclude we should draw at the 5% significant, what conclusions should we draw at the 5% significance level? Is there okay, so let's run that. So, all right, so if I go to hypothesis test, okay, we're testing against 7.5 on a mean. Okay, we have a sample average of 7 and the standard deviation of 2. Okay, they didn't tell us anything about the standard deviation from the previous study, so we have to go with a t-test in this case. Okay, so and how many did they say they drew? 100. Okay, and we're going to run a t-test because we don't know the standard deviation of the population. All right, and this is a two-sided test, so we use the 0.14. That is definitely under 5% because this is 1%, and we reject when the p-value is less than the significance level, okay, or the alpha level, however you want to describe it. Okay, so let's find the one that has us reject at that spot. There's convincing evidence that the mean time has changed. Yes, that is true. Not convincing evidence that the mean time is still 7.5. No. Convincing evidence that the mean time is now 7. No. When we're doing a test on the mean being or not being 7.5, it doesn't mean that we accept the alternate. It just means that we think that it's not 7.5 anymore. Okay, and we cannot draw conclusions that's not true. All right, 10. All right, are TV commercials louder than their surrounding programs? To find out, researchers collected data on 50 randomly selected commercials in a given week. With the television's volume at a fixed setting, they measured the maximum loudness for each commercial and the maximum loudness for the first 30 seconds of regular programming that followed. Assuming the conditions for inference are met, the most appropriate method for answering a question of interest is what? Okay, so in this case, let's see what we've got here. A 1 proportion z-test, a 1 proportion z interval, a paired t-test, a paired t-interval, none of these. Okay, so if we are choosing channel 2, okay, then we're going to have two pieces of data for channel 2. We're going to have its commercial and then it's not commercial, okay? And we've got the maximum volume of each, which we would subtract to get a difference. We would do the same thing for channel 4, same thing for channel 7, and so on. We would take their commercial minus their not commercial, and this is a paired t-test. So that would be the best way to run that study. Okay, looking at 12. All right. Can't get through my day without coffee is a common statement from many students. Assumed benefits include keeping them awake during lectures and making them more alert for exams and tests. Students in a statistics class designed an experiment to measure memory retention with and without drinking a cup of coffee 1 hour before a test. This experiment took place on 2 different days in the same week, Monday and Wednesday. 10 students were used. Each student received no coffee or 1 cup of coffee. Okay, so each student received, so we've got 2 different days. They either received no coffee or coffee 1 hour before the test on the particular day. The test consists of a series of words flashed on a screen, after which the student had to write down as many of the words as possible. On the other day, each student received a different amount of coffee, either none or a coffee, and they would probably repeat this study. All right, one of the researchers suggested all the subjects in the experiment drink no coffee before Mondays and then 1 cup before Wednesdays. Explain to the researchers why this is a bad idea. It's a bad idea because it might matter Monday versus Wednesday. Okay, so one's the day right after the weekend, so their sleep cycles might be different. So again, Monday and Wednesday could matter, and if you don't split it up and do half and half, then now you've got a lurking variable, and you end up with confounding at the end of the study. All right, here's the data from the experiment provided in the table below. Set up and carry out an appropriate test to determine whether there is convincing evidence that drinking coffee improves memory. Okay, so we want the differences. So all of these values would go into L1 and L2 like I've already shown. Okay, we would define our null and our alternate. Okay, in this case, our null, okay, is that the mean difference is 0. Okay, and we want to show that coffee makes them more alert, so they do better. The assumption is they do better using the coffee. So if we're going to subtract them in this order, the no cup versus the cup, okay, if this is better, we're subtracting a bigger number, we end up with negatives.
Caleb Perry come to the office, please? Mason McGilvery and Caleb Perry, please come to the office.
So mu of the difference is the true mean difference in score, and it is basically not coffee versus coffee. Okay, so a negative in this case means that coffee did better. A positive in this case means that no coffee did better. All right, so when we run this test, we find that x bar equals -1 with s of x equals 0.816. Okay, and that gives us a t interval of -3.875 and a p-value, which is a one-sided, of 0.0019. Okay, so at any of the alpha levels we've been used, typically we use alpha equals 0.05. Our p-value is under our alpha level, therefore we reject the null. So make sure you put a conclusion there that says we reject the null, and we describe it, and it appears that the coffee drinkers are doing better than the non-coffee drinkers. All right, the last one. A government report says that the average amount of money spent per U.S. household per week on food is about $158. A random sample of 50 households in a small city is selected. Their weekly spending on food is recorded in this table. All right, and there's no outliers. Okay, explain why the normal condition is met in this case. Okay, the normal condition would be met since our sample size is greater than 50. There's no outliers. Can you conclude that the mean weekly spending on food in this city differs from a national figure of 158? Okay, so is 158 inside of the interval? And it is not inside of the interval. And since it is not inside of the interval, we would reject that null. Okay, so again, our null would be that the mean is 158, and the alternate would be that is either not 158, we can just run it that way. And since it's not in the interval, we reject the null. All right.